Hello everyone and welcome back to my channel Gyan Sampada. We have already discussed many properties and simple applications of quantum mechanics. So while doing so, I just had a thought of explaining the most basic concept in quantum mechanics which we'll be covering in today's class. So today we will be studying about the basis as well as the dimension, and if we need to study these we need to know two things. One is the linear independence and another one is the linear dependence. So our flow will be in this order and we will understand all these concepts using some basic examples. So let's start our today's class on quantum mechanics, or we can say especially dealing with the vector space. So first we will be dealing with the linear independence or the linearly independent vectors. So what actually is linear independence? Independence means we can say that each vector or the parameter is not depending on each other. So how to define these things, let us study. For that, let us consider a set of non-zero vectors phi1, phi2, phi3 so on up to phi(n). And we can write the linear combination of all elements as summation over 1 to n ai phi I is equals to 0. So when we are having a set of non-zero vectors, say phi1, phi2 so on up to phi(n), it is said to be linearly independent if and only if the solution of this equation, whatever we are seeing here, is a1 equal to a2 equal to a3 so on up to an is equals to 0. That is, we can observe that these coefficients are going to vanish, which means that no vector in the set can be expressed as linear combination of other vectors which are present in the set. So each vector is unique in itself. It cannot be represented with respect to another vector which is present in the same set. So that is what is called as linearly independent vector. Thus we can say that the set will not contain the same vector twice. So there is no repetition of vectors. So if we need to define it, we can say that the linear independence is the property of a set having the linear combination of all its elements equal to 0 when the coefficients are taken from the given set unless the coefficients of each element is 0. That is, whatever we have discussed here has been put in the form of statements. So first is about the linear combination which is represented using this equation, and the second part is expressed with respect to the coefficients of each vector. That is a1, a2, a3 so on up to an, and that is going to be equal to 0. So this is how we can explain about linear independence. Let us understand using one example. Say v1, v2, v3 so on up to vr are the vectors which belong to r raised to n, where each is having the standard meaning, and it is linearly independent only if the scalars that satisfy this equation is nothing but the same thing, the vector sum of its components. So a1 v1 plus a2 v2 plus so on up to ar vr is equals to 0. Here each vector is associated with a coefficient and its solution, that is the coefficients a1, a2, a3 so on up to ar, each and every term is going to be equal to 0, and thus such a combination is called as trivial linear combination. And this is what we observe in linearly independent vectors. So this is one part. Now let us move on to the second part, which is about linear dependence, or the corresponding vectors are called as linearly dependent vectors. Again the same thing we are going to consider. We will consider the set of non-zero vectors. Then again if we consider the linear combination of all its elements, then the solution need not be equal to 0. That is, if there exists a set of scalars which are not all equal to 0, so that one of the vectors, let us say phi n, can be expressed as the linear combination of others, then such a set phi I is said to be linearly dependent set. And that vector can be written as phi n is equals to summation over I equal to 1 to n minus 1 of ai phi I plus summation over n plus 1 to n ai phi I. So it is something like superposition principle itself, where we are writing one vector as sum of two vectors of the same space. And this is about linear dependence. So the same example we will consider and we will see what is the difference. So if we consider set of vectors v1, v2 so on up to vr belonging to r raised to n is said to be linear dependent only if the scalars which satisfy this equation, that is the sum of all its components, are a1 not equal to 0, not equal to a2, so on not equal to ar. So such a combination is called as non-trivial linear combination, where we can say that the coefficients are not going to be equal to 0 and these can be written in terms of the other coefficients also. Like we can write a2 in terms of a1 or a4 in terms of a5, like that. So we can say that one of the vector can be expressed as the linear combination of other, because the coefficients associated with those vectors are going to be interrelated. So that is the case which explains linear dependency. So this is, we can say that, the theory part which explains about linear dependence and independence of the set. If you need to know exactly what actually it is, then we can consider a very simple example for a better picture and better understanding. So for that, let us consider three vectors. Vector A is equals to 2i cap, vector B is equals to 7j cap, vector C is equals to 5k cap. So here 2, 7, 5 all are the magnitudes of the vectors, and I cap, j cap, k cap are the unit vectors along corresponding directions. We can say along x, y and z direction respectively. And if we want to know about the dependency or independency, we need to consider the linear combination of the vectors. So I will consider a1 into vector A plus a2 into vector B plus a3 into vector C. So here a1, a2, a3 are the coefficients which are associated with the vectors a, b and c respectively. So in place of vector A, we will substitute 2i cap. In place of vector B, we can substitute 7j cap. In place of vector C, we can substitute 5k cap. And if we need to check whether it is a linearly independent or a dependent case, then we can say that this equation has to be equal to 0. So this is like the summation of all the component vectors equating to 0, which we have already seen in previous slide as summation from 1 to n, an phi n equals to 0. If these components equal 0, then we can say that it is linearly independent. If it is not equal to 0, then we can say these are linearly dependent. So let's check it out. Clearly we can say that this equation has three parts, and if the sum of all three has to be equal to 0, then each of the term has to be equal to 0, because here none of the term is having any common thing. Like a1 is not equal to a2 nor equal to a3. Also the magnitudes are different and directions which are denoted by the unit vectors are also different. So directions can be considered or just left. So here, if we want to solve it, we can say that 2a1 I cap equals 0, 7a2 j cap also equals 0 and 5a3 k cap is also equal to 0. Then only the sum can be equal to 0. So when we do that, we can observe that 2a1 I cap equal to 0 means a1 is equals to 0. Similarly here a2 will be equal to 0 and finally a3 is also equals to 0. So we can say that this is forming a linearly independent set of vectors. So I hope the picture regarding the linear independence is clear. Now let us move on to linear dependency. So I am going to consider two vectors. Vector A is equals to 6i cap minus 9j cap and vector B is equals to 3j cap minus 2i cap. Again considering the linear combination, that is a1 vector A plus a2 into vector B, which will be equal to a1 as it is. In place of vector A, I have substituted the value again similarly in the second part. Now I will be collecting the terms with respect to their unit vectors. So 6a1 minus 2a2 will be taken into the brackets and I cap is common outside, plus when you take j cap common, we have minus 9a1 plus 3a2. Again, if the sum of two factors have to be equal to 0, it means that each factor have to vanish. So we can say that first part, that is 6a1 minus 2a2 has to be equal to 0, and when we rearrange we can say that 6a1 is equals to 2a2, so that a1 will be equal to 2a2 by 6, which is nothing but a2 by 3. And similarly, if we consider the second part, we can observe that minus 9a1 plus 3a2 is equals to 0. And when we rearrange this, we get a2 is equals to 3a1, which is nothing but a1 is equals to a2 by 3 itself. So here clearly we can observe that one coefficient a1 can be expressed in terms of a2. Thus, we can say a vector can be written in terms of the linear combination of other vectors, which is going to explain about linear dependency. So this example 2 explains about linearly dependent vectors. So I hope by solving this example, the picture regarding linear dependence and linear independence is clear. So with this basic, we will move on to our next topic, which is the main focus, nothing but basis. So as such, basis, we can say it is like a foundation or the very fundamental thing. So what actually is a basis in case of quantum mechanics is the question. So let us have a brief discussion about it. So let's see the definition of basis. We say that the basis of a vector space consists of a set of maximum possible number of linearly independent vectors which are belonging to that space. So it is something like a collection which consists of all the linearly dependent vectors. So it is something like a universal set where we will be having different components. So the set of vectors phi1, phi2, phi3 so on up to phi n to be denoted in short by the symbol phi I within the flower brackets is called the basis of the vector space, while the vectors which are contained in it, that is phi1, phi2 so on up to phi n, are called as a base vectors or else basis vectors. So can we choose any arbitrary thing as a base vector or it can form a basis is the question. So we can say that if we want to work out more conveniently to get a better results, then it needs some of the conditions to be satisfied. There is a requirement of satisfying some of the conditions for forming the basis. So although the set of these linearly independent vectors is arbitrary, it is convenient to choose them orthonormal. That is, their scalar products should satisfy the relation which is seen here. And the relation or the condition is the inner product of the components, that is phi I with phi j, is equals to delta ij, where delta ij is the chronicle delta function which will be equal to 1 if I is equals to j, that is for the same basis vectors, and it will vanish if I is not equal to j. So we can say that a set of vectors here are to be orthonormal, and these set of vectors are called orthonormal when every vector is normalized to 1 and for every two different vectors their inner product is 0. And the basis is said to be orthonormal if it consists of a set of orthonormal vectors. So based on the components of the set, we can name the set. So if the vectors whichever are present are orthonormal, then the whole basis is said to be orthonormal basis. This is one condition. And moreover, the basis is said to be complete if it spans the entire space. That is, there is no need of introducing any additional base vectors or basis vectors. So clearly we can say that a quantum mechanical basis can be thought of as a set of orthogonal vectors with a specific dimension, and these are usually chosen so that their magnitude is 1, and the main factor is this, that is, the set of basis vectors spans the space, means that every dimension has a vector pointing in that direction, but there is no extra vector present over there. So we can say that there is a one-to-one correspondence between the basis vectors and the dimensions of the space. In mapping of the set, we generally observe this one-to-one, on-to correspondence and everything. And here we can see that there is a one-to-one correspondence between the basis vectors and the dimensions of the space. So generally, a very simple case of basis set is the set of ijk or xyz, that is the three-dimensional space. So any vector in the space can be written as the linear combination, like vector q can be written as ai cap plus bj cap plus ck cap, like that, where a, b, c will be the scalars which can be immediately recognized as the components of vector p along the three Cartesian axes. So in three dimension it is very simple, but the things are little more complicated in quantum mechanics, as the state vectors which describe the system is expressed in the Hilbert space. And Hilbert space have many dimensions. We can say that an infinite dimensional space. So the scalar components can be complex numbers also. So finally complications arise, but generally the idea is going to remain the same. So this is about the basis. Now let us move on to the next concept, which is again important, which we discussed here, that is one-to-one correspondence between the basis vectors and dimensions of the space. We have understood what actually are the basis vectors or base vectors. Now let us understand what actually is a dimension of the space. So it is having the usual meaning. So let's consider the wave function xi, which can be written as the vector sum of its components, that is summation over I equal to 1 to n ai phi I. Let us call it as hash. That is, the vector xi can be expanded as a linear combination of phi I in n-dimensional space. Phi I can be phi 1, phi 2, so on up to phi n. So with respect to these components, we can express xi, and the space will be n dimensional. So here the dimension word is coming. So what actually it explains? We can define a dimension of a vector space as the maximum number of linearly independent vectors the space can have. So here we can say that this capital N explains about the dimension of the space. So the expansion coefficients AI in hash are called as the components of the vector xi in the basis. And each component is given by the scalar product of xi with the corresponding basis vector, which can be given as Aj is equals to inner product of phi j with xi. Similarly, Ai will be equal to inner product of phi I with xi. So in this manner, we can also find out the components, which are nothing but the expansion coefficients. So clearly we can say that a basis consists of the basis vectors. These basis vectors are forming a set of are orthonormal, and the basis is also complete if it spans the entire space, and the maximum number of linearly independent vectors in that space explains the dimension of the space, and the coefficients whichever are present are called as components, and that component can be found out by considering the inner product of the wave function with its basis vector, that is phi j with xi. And these are some of the details about the basic concepts of quantum mechanics, and I hope that you found it helpful for you. So if you understood the concept and got some knowledge, then do like it and also subscribe to my channel, and I will be happy if you share some suggestions for upcoming classes. So stay tuned, study well, and thank you for watching.